In this video, we will talk about logistical regression. Logistic regression essentially is a parametric way which tries to classify a binary categorical variable into a 0-1 class based on a set of explanatory or independent variables. So why a new method? Why can't we use linear regression to undertake this exercise? For this example, consider a data set which gives us Oscar nominations and Oscar winnings. If in this data set we were to simply run a regression model, now first of all let's observe that we have some observations which did not win the Oscars, and then we have some movies that won Oscars, right? So they can be either a winner or a non-winner. Suppose we want to develop an algorithm to predict winners of Oscar based on nominations. This algorithm will come up with a probability score, and we can use this probability score based on a cutoff to classify a record as a winner or a non-winner. Now there are various ways in which we can get these probability scores, but what we cannot use is a linear regression. Why? Suppose we run a linear regression and we try to predict a probability value running this linear regression. A linear regression by nature is not constrained to lie between a given bound. For example, in our data set, when we run a regression model, our regression equation, or regression line, which is given by the blue line and is minus 0.405 plus 0.08 times nominations, has some values which are predicted to be negative. Probability, however, has to lie between 0 to 1, but nothing constrains regression line to have a probability outcome predicted that is between these bounds. So this renders regression unsuitable for a classification task. We can also see this if we were to plot the residuals of a regression against the predicted values. And residuals here have a clear pattern, which again implies that regression model, the way it is not appropriate to engage in a classification task. Logistical regression, on the other hand, is a technique that is used in literature very frequently. Logistical regression is based on the idea of odds. We are estimating odds of an event. Odds are essentially given as a probability of that event occurring divided by the probability of failure. So probability of success over failure is considered odd. And the odd metric will lie between 0 to positive infinity. Now this unbounded nature can be captured, can be taken care of by estimating a log version of this. So the logistical model will essentially estimate the logs of odds of an event occurring as a function of various x's that we are given. Let us see an example to understand the concept of odd and log odds. Suppose the probability of an event occurring is 0.2 or 20%. The odds are given as a probability of success over probability of failure. So in this case, it would be 0.2 divided by 0.8, which is 0.25. If we take the logs of it, we get log odds. Log of 0.25, or natural log of 0.25, is negative 1.3863. So while odds are 0.25, the log odds are minus 1.3863. From the odds, or from log odds, we can recover back probability. And that's done by essentially transforming this to isolate p and then get p. So we can take the inverse, we get 1 over odds equals 1 minus p over p, and then we can simplify and clear out the equation, and we will get p equals odds over 1 plus odds, or 0.25 divided by 1.25, which is 1/5 or 0.2. We can also obtain the same thing by using this equation. Again, notice that if log odds are minus 1.3863, then odds are exponential of minus 1.3863. So we can then plug this in this equation and we will again get a value of 0.2. So the logistical regression is essentially estimating the log odds of an event as a function of the various independent variables. We can examine this by looking at the equation for logistical regression. So this is the odds. When we take the log, we're estimating the log odds as a linear function of the various independent variables. So once we get the value of b0, b1, bx, we can plug them in and into this equation, and we can revert back and recover the value of p hat. It is this p hat which will now be lying between 0 to 1. And we can use a cutoff to then classify a record as either belonging to class 1 or to class 0. So to see this, if we were to plot the probability values, we would get a curve like this. So this is the logistical plot of the same data set. Whereas when we did a linear regression, our data set had probability values being predicted to be negative. The logistical regression will constrain the values to lie between 0 and 1. And then we can, of course, use our cutoffs to then classify a record to belong to one or the other class. In real life, we may have a lot of variables. Do we include all of them in running a logistical regression? Well, those questions are very similar to what we do in multiple regression, where we might use some subject matter, we might rule out variables which are highly correlated with each other to avoid multicollinearity, and we might find some metrics like a malus C or log wort or some other measure to see that we can include only the variables that are having a strong predictive power in our problem of interest. But the idea is still the same, that when we are trying to classify a record into a 0-1 group, or even in multiple classes, a linear regression might give a probability value which could be less than 0, or it could be more than 1, and that renders it unuseful. Now, once we have obtained our coefficients of the various parameters and obtained the probability value, we can then use a cutoff to get a table like this. So each record then comes up with the value of the probability. So the first example we have is a movie that had 40 nominations. The probability of winning is 0.89 based on the log logistical regression that we ran. And if our cutoff is 0.5, then because 0.89 exceeds 0.5, the movie will be classified or predicted to be belonging to the winner class. And were we right or wrong? This movie actually was a winner. But then a model will also be wrong sometimes. For example, here, the third observation, this movie had 10 nominations. Based on the 10 nominations, the winning probability is 0.44. And because this is less than 0.5, this movie is classified as a loser, and it was a loser. However, look at this last observation. Here, this movie had only 6 Oscar nominations. Based on our model, the probability value that will be predicted will be 0.07. This is much less than 0.5, so our model would classify this record as a loser. But this movie, in fact, was a winner. Our model got this prediction incorrect. In fact, our model predicted this to belong to class 0, but this movie was actually a class 1. So this is an example of a false negative, where the model predicted 0, but the actual class was 1. And we can run this for the entire data set, and we can then get a confusion matrix with which we can assess how well a logistical regression does against some other competing models. And even within logistical regression models, we could then do some variable selection if we had a lot of variables and see which of these models actually gives us a higher either AUC or area under the curve, or a higher F score, or a better lift chart.